Aloha, Richard Halverson here. This is ITS228. Excuse me. And today is February 17th. Let me share my screen. Let's see. This one. And so we are in here staff, or we're still okay. I think what I said is I was going to start hash tables this week, and that's why we because we're pretty much done with stacks and queues, and I've explained the assignment. So let me make sure. Yes, I did. This one, assignments. Yeah, stacks and queues. Okay, so I can tell you a little bit about what my idea is for the fourth assignment. It's in chapter. It's stacks and queues. Let's go. It's hash tables. So let's learn about hash tables. It's a very important data structure. So a hash table is a data structure that stores unordered items by mapping them into a location. Okay, so you use a hash table to store stuff. You map it to a location, and then when you want to retrieve it, you can use that mapping to go get it, and then presumably the mapping operation is just one unit of time. See, so a hash table's main advantage is searching for inserting or removing. Searching may require, best case, order of one operation, whereas if you're searching linearly, it's you possibly may have to look at every single item before you know whether it's even in the list. Or if it's a binary search, if the list is sorted, then you can do it. Then you can find out in O of n log n if the item is in there or where you would insert it, for example. And so a common hash function is just to take the modulo of the key, and that will map into a value, and that's where you store it. And that makes sense until you have two things that map into the same place. And so hash tables, this whole chapter is all about when you have two things mapping into the same place, how you handle that. Okay. So here's a little example of a hash table and a structure. And so it looks like we have 10 slots, and we're hashing in, or we're storing these numbers. And so we're going to use modulo 10. The hash function is the key, which is this, like this number or this number or this number, key mod 10. That's the hash function, and that gives us a number, and that's where we're going to store it. And if there's a collision, then we are going to have to do something about that. So let's see this work. We start out where we define a hash table that's got 10 locations. And the first thing we do is we store in 116, and that's going to go into slot 6 because, 116 mod 10 is 6. And then we're going to store in 12, and that's going to be in the slot 2 because mod 10. And then we're going to store in 23, and that goes there. And then we're going to search for 23, and we see that the hashing is 3, and so we go there. There it is. You see, that's how we go. Okay, so we searched our hash table for something, and it was not a binary search. It was not a linear search. It was just one calculation and there it is. See, so that's the potential of a hash table. So the clever part is choosing the right hash function and you know, size and so on, and then also selecting the right method for handling collisions. So this just goes on to say that in this chapter, a number like item 64 can actually be a record of some sort or an object, but we're just really concerned with the key value. See, so all right, so common hash function uses the modulo operator, and it doesn't have to be you know, a multiple of 10 or 100 or something. It's, in fact, it's better if it's some sort of odd number. In fact, it's best if it's some sort of prime number, because then the chance of you getting collisions is reduced in theory. All right, so here's this just tests to make sure you understand what all these terms are. How many buckets will be checked for hash search the table for 45, and so that that maps into 5, and so it's just how many buckets are checked. It's just going to be 1. If item keys range from 0 to 49, how many keys may map into the same bucket? How many keys? There must be some other parameters here. I'm not sure what it's asking. All 50 keys map in the same bucket. Oh, I see. Oh, I see. We're still, I thought this was defining the size of the table. I was reading this wrong. I thought it was defining the size of the table. And really what it is the key values range from 0 to 49. We're still using this table. And so, the fact that it's 50 of them, and it's so it's 0 to 49, if we, at most 0, you know, at most, any bucket would have the one for for 0 as the first digit, 1 as the first digit, 2 as the first digit, 3 as the first digit, and 4 as the first digit. So that's what that is. Anyway, sorry. All right, so now we're going to start talking about collisions. And for collisions, one method, that occurs when two items map into the same bucket. And so like if you have 55 and the table size is 10, that maps into 5, and 75 also maps into 5. Chaining is when you have a bucket is actually a list of items. So the 55 would map into a list that's hanging off of bucket 5, and 75 would be, you know, inserted onto that list also. For open addressing, it would go to, if 55 got there first, and then it came time to map 75, 75 would notice that that 55 has already taken slot number 5, so it checks slot number 6. And if that's taken, it goes to slot number 7, and it keeps on going until it finds an open slot. So remembering all this, when you're searching for an item, to find the data or to remove it, you have to consider these things. And so you have to, the way you handle collisions is the same the algorithm for looking in the next slot or putting something in the next slot has to be the same for inserting as it is for searching and removing. Okay, so that's pretty simple. All right, so you can do that. I'm not going to try to do these because I always make mistakes. All right, so here's chaining. Here's an example. It's describing these algorithms in this algorithmic language. That's not really any language, but you should learn how to read this algorithmic language and know how you would translate that into Python. In fact, the very end here, it does it for you. But as we will see again, in chaining, for example, this list data structure that it describes in Python describes it in a way that uses lists like it is here, where you've got nodes and links to the next node. And of course, in Python, we have a list data structure that works fine. And so I'm going to have you, the next assignment, I'm going to have you implement the hash tables here. We're talking about chaining right now, but let's go to the hash tables, the Python hash tables. And here this describes the Python versions of all of the code and classes that are described in this chapter. And chaining, which is one way of handling collisions. And they all have an insert, a remove, and a search. And open addressing bucket, open addressing bucket class, and for inserting, removing, and searching, it's the same thing. It goes on to the so you can see how that works. Here's linear probing. I think I might have gotten this. Okay, so we have linear probing, quadratic probing, and double hashing. Okay, so these are three different ways of handling collisions. Linear probing is just going and looking at the next one, searching from where the collision occurred. From there, just going step by step, looking to see the next closest one that's open. With quadratic probing, you aren't just going to the next one. You're using a fancy formula. Do we have that here? Anyway, here they all are. 1, 2, 3, 4, 5, 6, 7, 8. So you're going to download all these and look through them and get them running. And so this shows the code. This is one that you're going to change, the shading hash table. Well, first you're going to get this to work, and then we don't need to implement the list the way it's implemented here. We can take more advantage of Python data types. And so all these are here. All of the ways of probing through quadratic hashing, instead of going to the next one, it uses a formula that's got two parameters, and it skips. And each time there's a collision, it skips a greater distance, and it skips in kind of a way that there should be some, where to reduce the number of collisions. double hashing just means you use two hash functions. There's two separate hash functions, and you have hash function number 1, hash function number 2, and you know, each time you have a collision, this is incremented by 1, and it's you know, it greatly reduces the chance of there being 2 collisions in a row. And then so I'm going to have you do that, and I'm also going to have you implement hash table resizing. So that'll be in the next assignment. But we were talking about chaining, so I'll just go through these for you. And it's a good idea to understand how they work, because when you're going to implement them, the Python programs, you want to see what's going on, and there might be some things that you might want to change a little bit. All right, so here's linear programming, which handles the collision by starting with the keys mapped bucket and then linearly searches subsequent buckets until an empty one is found. And so here, for example, let's see what this looks like. So we're going to start with 124, and that goes there, and there's a collision. So it's just going to, it goes to the next one, which is empty, and that's that, so it puts it there. And then there's another collision. No, that's a search. That's how searching works. We're searching for 124, and that's returned. And then we're gonna search for 33. It's not that. It checks that. It's not that. Checks that. It's not that. It checks that, and that's empty. So it must not be. So it's not there. All right. There's a caveat to this, which. Okay, so now this is the caveat. There are empty bucket types. Okay, there can be buckets can be empty because there was never anything put in them, or a bucket can be empty because there was something put in them, but then it was removed. It was removed by a remove function here. And so you have to know that, because, for example, in this case back here, when we were looking for the 33, we stopped at 6. With 6 was empty, so we thought, oh, okay, we didn't find our 33. Well, it's possible that the 6 could have been empty because it's possible that if there was like 64 was inserted, if 64 was inserted, that would be down here. And then if 33 were inserted, that would be down at 7. And then if 64 were removed, this would be empty. And so we'd have 6 being empty, and we're looking for 33, and 33 is actually here. It's at 7, but we only searched to 6. And so that's not sure they should have demonstrated this example before they talked about the case of a cell, a bucket can be empty from the start, or it can be empty because it's after a removal, and so you need to keep track of that. You need to be able to look at an empty bucket and know if it's been empty since the start, or if it's empty because there was just something in there and then it was removed. All right, so go through this step by step to make sure you understand that concept. Inserts using linear probing. Okay, so here, this is the algorithm where you figure out what the bucket is, and you check to see if that bucket is empty. If it's empty, you have a place for it. Otherwise, if it's not empty, you have a place for it, and then you're done, so you return. Otherwise, if you make it down to here, it means that the bucket was not empty. So we increment the bucket index by 1 mod n, that's mod the size of the hash table, and then we go back and we try again. We see if that's empty, and we keep on doing that until we find one that's empty, and we keep track of how many that we've probed. So anyway, that's linear probing. Removals with linear probing. First, you want to find it. Hash key. If it's the hash table bucket is not empty since start. Okay, so this is a condition to stop the loop. If it is empty from the start, then we know, and we haven't found it yet, then we know that. So here we're looking for it. Here we're looking for the key value that we want to remove. So we loop, and if we find it, then we set it to empty after removal. Okay. You know, the state of it. The state of it is empty after removal. So it's gone, and we put it in this state, and then we return. Otherwise, otherwise we have to move on to the next one, and it's not you know, we keep on looking until we find a bucket that's not empty, that has the key value in it. And there's some sort of limitation here where buckets probed has to be less than the number of less than the size of the hash table, obviously. Okay. After you've looked at every single one, and it's not there, then you know it's not there. All right, so that's removal, and searching is this describes the searching algorithm. It's similar to the removal, except for you don't remove it, you just return the value item. All right, so make sure you understand that. Quadratic probing is a little different. It's just more complicated. Instead of you just moving on to the next one, you move on to, or the next one is by way of this formula. So you have this I is you know how many times you start with I equals 0, and you increment each time, you know, for a search each time each time an empty bucket is not found, if you're probing to insert, when linear probing is just C1 equals 1 and C2 equals 0. Okay. If C1 equals 1 and C2 equals 0, then that's exactly what linear probing is. But with quadratic probing, we add this square term, and the coefficients of the I term and the I squared term can be different than 1. Okay, to make the jumps longer or whatever. And so, so this is the formula for quadratic probing, and so it's the same as linear probing, except for you're not going right to the next one, you're going to the next one according to this formula, the index of it. And this here has you make sure you understand that. And again, there's always an insert, a remove, and a search. So this is the one with quadratic probing. And this is where the formula is. And so you're gonna, put something there. You're gonna put some constant value there, some constant value there. And then, these are just i's. This is I. It starts out with I equals 0, I equals 0. And each time you have each time you find a bucket that's not empty. This is for if you're trying to insert. Let's see, for this is when you're looking for it, each time you miss, then you increment according to this formula. And if we were to make this a 1 and we were to make this a 0, then this would be the same as linear probing. All right, double hashing just has 2 hash functions, and then you have your key, and you take, this is your first hash function, and then you have this second hash function, which you multiply by the I and mod the table size, and that's how you probe. So that's just another way. All right, hash table resizing. You should study this section, because I'm going to have you write a Python program to do hash table resizing for one of the hash table probing methods in in the set of these algorithms that you're going to implement in Python here. Okay, so you're going to implement these here, these on your server, and it may be the chaining one, because I'm going to have you mess with the chaining one anyway, and I'm going to have you, although the chaining one, there might not be that much of a necessity to do table resizing, but I don't know, we'll see. Maybe not chain. But I'm going to want you to go write a function where you're going to take the hash table and make it bigger. Now, that's there's not really a data structure in Python where you're limited from the time that the program begins executing. I mean, you don't declare fixed size arrays. You would never declare a fixed size a hash table, but you may be emulating some sort of, I don't know. Anyway, I'm going to have you adapt this hash table resizing algorithm to the you do have to, you would want to have various sizes and actually specify size in Python for the hash table, because you have to always do that modulo operation, right? So anyway, when you resize, you have to create a new hash table and then rehash everything that's in the current hash table. You have to rehash it into the new bigger hash table, and so so that's the algorithm that you're going to have to implement. And that's probably what this is. And you're going to implement a Python version. That's all. All right, so so this talks about when you may want to resize. So it talks about a load factor, how much filled up is the hash table, and you know, this might be, yeah. So let's say the resize, let's say you're doing chaining. The resize criteria is when the bucket lengths get to be greater than 4. So so here we are, and this is, we're chaining, and this one's getting pretty big, and let's say that it's time to resize, and then so you decide, instead of 0 through 4, instead of a 5 sized hash table, you go to an 11 sized hash table. That's weird. Oh yeah, no, that's right, that looks good. Yes, it's 11. So yeah, so 33 maps into 0. Okay, yes, it works. So anyway, very interesting. So so make sure you understand this. And so I'll probably have you put something in your program, or maybe it'll be a parameter or something. Here we talk about common hash functions, and you know, we've been talking about modulo all the time, but I think there's other ones, and you can look and understand these. I probably won't have you implement any of these, but I might. And we always compare it with the perfect hash function, which is it's O of 1, no collisions. There's never a collision. Now you can make that by doing direct hashing. Trouble is, you have to make sure that that by design you have a hash, you have a bucket for every single key. So you know, that's just an array. You know, that's just a, I mean, that's just a memory where the address is the key. The address is the bucket. And so so this talks about that direct access table. It's just very simple, but it can be expensive. Okay, this talks about cryptography and password hashing, other uses of hashing. Here, this thing called the Cipher is where you take like every, you know, the ASCII character set. Oh, let's see, where was that? Was there? That was in hash functions. Yeah, this is what's called the ASCII character set, and so this is the mapping of the capital letters to the decimal value, and the decimal values actually go from 0 to 127, and the lowercase letters are down, well, they're either lower or higher. We can search for them, but so with these in mind, when we talk about, okay, so A is 65, 66, 67, 68. So you can see that it goes up like that. And with the way the Caesar cipher works is you say that each letter we're going to shift right, you know, 4 by 4. So capital N becomes OPQR, capital R. So there's capital R as the first one, okay? And then this lowercase e becomes lowercase I, and then the W becomes this left curly brace. And so if you look at the ASCII character set, you can see, you know, numbers from 0 to 128 or 127 or 0 to 255, and you could create a cipher that that does it that way here. And so one thing about this kind of cipher is that you can get the original message back by knowing what the cipher is. So if you know you do shift 4 right to get the encrypted message, and then you do shift 4 left to get back the original message. Now there's so with these you can go both ways, but hashing of data is often used where you don't ever plan to go in the other direction. Okay, you use the function, the hash function of going in one direction as a way to verify something is an original, but if you have the hashed function, the hashed result, the hash, you can't go back into the original message. And so that's what they're talking about here. This MD5 produces 128 hash value for any input data, and so so you know you have a message, you know, that's written like this, and you run it through this MD5 hashing thing, and it produces this, and then you download the message and you run it through this MD5, and if it's not the same as what, you also send this. If it's not the same, then you know that the message was corrupted. So anyway, they use password hashing the same way. When you type in, when you log in, and the system checks to make sure your password is correct, it doesn't have a copy of your password. It has a copy of a hashed version of your password. And so when you create your password, it stores a hashed version, and whenever it wants to verify your password, it takes what you type in and runs it through the hash function, and it's got to be the result has got to be the same as the hashed version that it originally stored. If it's not, then you haven't typed in your password correctly. Now, of course, it's possible that two different, completely different, passwords, map to the same hash function, but that's highly unlikely. All right. So here, okay. So we've talked about all that, and here in this section 5.10, we have hash tables, or we have Python versions of all these functions, and so next time I will. I haven't written the assignment yet, but next time I'll have the assignment written, and we can go over it then. So that's pretty much all I have today. Do you have any questions or anything? Very good. Hearing none, I will see you next week.